The next talk is from Antonio and Daniele. I don't know who is going to present.
Yeah, I'm sharing the screen. Just a moment.
Perfect. So
okay.
This is a pre-registration paper. But okay, so thanks, Antonio. Thanks for presenting this. All yours.
Okay, so hello everyone. I'm going to present to you CDIMM, the benefits of domain-based mixture models in Bayesian continual learning. So the ideas of this paper are twofold. On one hand, we want to show how some assumptions that we typically make in continual learning are broken by real-world streams, and they are very problematic. And on the other hand, we want to argue that non-parametric Bayesian continual learning models are a natural solution to deal with these issues and to learn on very general real-world continual learning streams. So in continual learning, usually we test on some simple toy experiment, simple toy streams, like a class incremental setting where you get new classes at every step, or a domain incremental setting where you get new domains at every step. Like here in the picture, imagine that the color is the class and the shapes are different domains. So these two scenarios are in a virtual drift setting. So what this assumption means is that while the model at each step only sees a partial view of the world, the actual world is constant. So there is a static distribution which doesn't change over time. Like here, it's visualized in the embedding space and split by domains. For example, think about natural images. If you have a dog, the concept of a dog is constant over time. So a dog in the present, in the past, or in the future is always the same thing. So in the real world, streams are a little bit different because yes, you get new classes over time, but you also get new domains and you get some repetitions. So you can see some classes that you have seen before and some domains that you have seen before. This is quite different from what actually happens in the toy settings that we use for our experiments. Like you can see an example here where we see like the green class, we see different domains over time, and then this yellow triangle which we see again multiple times. So it's also a form of natural rehearsal, which is very useful. In theory, since we have this natural rehearsal, the problem should be easier to solve. But actually, we argue that there are many methods that are designed for class incremental settings that don't even generalize to this easier setting. So the objective of this paper are to show some example of failures of methods, specifically for the case of Bayesian continual learning model, and to design a general Bayesian continual learning method that can solve continual learning on realistic streams, and to evaluate these methods on a set of realistic benchmarks to show how and why they fail. Now, I'm going to leave the stage to Daniele Castellana to show you the idea behind the probabilistic model.
Hello to everyone. So our proposal is based on the concept of mixture model. In the finite case, a mixture model assumes that the data distribution can be decomposed into a set of simpler distribution. So, for example, if f of s is a distribution of our sample s, a finite mixture model approximates this distribution as a summation, where each term on the right is related to a mixture component. So the mixture component represents the simpler distribution, the smaller distribution in the mixture model. The theta are the parameter of the mixture components, or the parameter of the simpler distribution that approximate the complex one. We also have a prior distribution that is the probability to select a mixture component. One of the key problems in finite mixture model is to the hyperparameter k, that is the number of components that are in the mixture model. So the results of the approximation is really dependent on the value of k, and in practice we don't know how many components do we need in order to approximate the distribution. So in general, it's an hyperparameter that is difficult to set. We can overcome this issue, allowing our model an infinite number of components. These are called infinite mixture model. So the key idea between the infinite mixture model is that we extend the finite one in a Bayesian fashion. So we add a prior distribution over the mixture component. In this way, the model has a mechanism to create new components when are needed from the data. So in this sense, the infinite mixture model can adapt the number of components directly on data. During the training, the number of components is always finite, but now it is not an hyperparameter that should be set before the training, but it can be learned during the data. Usually the learning is performed using variational inference or sampling. Go ahead, please. In the context of continual learning, mixture model has been used to approximate the data distribution. In particular, we divided all this approach in 3 categories. In the time-based mixture model, each component is used to solve a different task in the continual streams. The problem of this approach is that each portion can be as difficult as the whole data distribution. In fact, it can be that a task in the continual stream is has the same difficulty of the whole task, the whole data. In the class-based mixture model, each component is used to approximate the distribution of sample with the same class. In this approach, it's easy to understand the component to use to approximate a sample, in the case that we are assuming that the task is supervised. But the problem is during the training, because it can happen that the sample of the class C are divided into the different tasks in the continual stream. So the learning should be performed continually on the stream, and this can be difficult. In the last approach, instead, we define a different component for each domain. As far as we know, this approach has not been used in the literature, mainly because the domain is usually unknown. So the fact that we don't know how to assign the sample to a component, this complicates the training. So our proposal is to combine the class-based and the domain-based mixture model to define a 2 levels mixture model. So the first level is based on the class labels. So it is a finite mixture model, and it defines a different component for each class. The second level instead is on domains, and it is defined as an infinite mixture model. So this means that each component each model that represents the distribution of a class is modeled as an infinite mixture model, where each component is used to model a different domain. The fact that we use an infinite mixture model is because we don't know a priori the number of domains that are inside a class. Each domain is then modeled as a Gaussian component. In the next, the whole pipeline that we use in our that we propose for our model is the following. We use a feature extractor to map the input into an embedding space. And then we use our class domain infinite mixture model to predict the class of the embedding. The feature extractor is frozen, so it can be either random or pre-trained on a subset of the data, while the classifier, that is the infinite mixture model, our proposal is trained by leveraging variational inference. Also, we can also be trained in an online fashion using the stochastic version of variational inference.
Okay, so now I want to describe to you our hypothesis. Now we will not describe the models in the literature in detail here. You can find the details in the paper, of course, but I want to tell you briefly why we think they will fail. This is a pre-registration paper, so we didn't run the experiments, but just by looking at the models and how they work, we can make an argument that they will fail in our setup. So for class-based mixture models, so the ones where define a separate component for each class, models like DeepSLDA basically use a separate Gaussian for each class. This means that if you have a simple non-Gaussian distribution, you cannot solve the problem with DeepSLDA, because it assumes that the feature extractor is good enough to make everything Gaussian. Instead, if you use some model like the class VAE, which trains a separate variational autoencoder for each class, then you really cannot deal with class repetitions, because the VAE suffers from catastrophic forgetting. So what they do in the original paper is that they train on the class and then they freeze it. But if you have repetitions, and again, repetitions are helpful. Having repetitions make the problem easier, but you cannot use them in the class VAE because otherwise you get catastrophic forgetting. Instead, methods that factorize based on time, like CNDPM, do not account for multiple domains. So again, if you have a different repetition here, what the CNDPM will do is to make a new component to learn again from scratch this old distribution that should be already known. Again, because it cannot modify the old ones. Instead, our proposal, based on domain mixture models, is able to learn on very general streams, recognize all the domains, and use them even in the presence of repetitions. So the experiments that we plan to do are designed to stress the limitations of different kinds of mixture models that we showed to you. The first one is domain incremental moons. So the moon dataset, it's a toy two-dimensional data where we show arc of the moon over time, so that we can test whether the concept of the class will drift or will grow to include the whole moon. And then we take two vision datasets, so CIFAR100 superclasses and omniglot alphabets. For CIFAR100, so CIFAR100 does coarse classes like flowers and fine-grained classes like orchids, poppies, and so on. So we use the coarse class as the target, and then we use the fine-grained class as the domains. So we show orchids first, then the model is going to see poppies, and this is all mixed together with every class. So the model is going to see repetitions and new domains over time. Same for omniglot, but in this case, alphabets are the classes. So omniglot is a dataset which contains multiple alphabets and multiple characters for each dataset. So alphabets are the classes, while the characters are the intra-class variations, so the different domains that you find inside each class. So to sum up, we can say that Bayesian continual learning models are a very natural way to deal with continual learning, and especially non-parametric models, because they can adapt to the data complexity over time, like they can add new clusters, new mixtures over time. And our approach based on domain mixture models is more general than current proposal in the literature, and at least we think so, and we hope the experiments will confirm our hypothesis. I think this is also connected to something that was discussed in the previous talk. So humans are able to recognize a task and to know when to switch from one to the other. And this is something that comes very natural with Bayesian models, because Bayesian model can do the inference and tell you what is the probability that I'm seeing an old domain, because the model learned the distribution of that domain. So the second point that I want to make is to be very careful about assumptions in continual learning benchmarks. So when you work with a toy stream, you should be careful about not exploiting properties that are not really properties that you can see in real-world benchmarks, like the fact that you don't have repetitions. If you want to play around with this, we have actually a generator for Avalanche. This is the class incremental with repetition generator by Ahmed. So I want to close with this slide, which sums up our idea. So avoid class incremental settings and use real-world streams. Thank you for your attention.
Thanks, Antonio. Thanks, Daniele, for the amazing presentation.